So I was studying for my university's comprehensive exam. This is an exam that you have to take if you're a physics PhD student. You write it, and if you pass, you get to stay a PhD student. I was looking at past year exams, and they had this beautiful quantum mechanics problem. And on the exam, you could only solve it about halfway. But using a computer, you could get these beautiful results of this problem. And we're going to look at this problem today. The problem is actually very simple. You have an electron localized near the origin in one dimension with a given wave function, and you have a detector far away from that particle. And then you ask the question, what's the probability of that particle being found beyond the detector as a function of time? There's sort of a very basic approximation method you could use to solve this problem, using a little bit of classical mechanics, but there's also the exact way to solve the problem, which involves the heavy machinery of the Schrodinger equation and getting integrals that you can't solve by hand, but that you can solve using a computer. So I thought, well, this is a perfect excuse for a YouTube video. As always, if you enjoy these videos, please be sure to like and subscribe, join the Discord server as well, and enjoy. So for the packages today, we have NumPy for all the numerical stuff we'll be doing, classic for Python. We have SymPy for all the symbolic algebra we'll be doing. This will be super helpful for solving this problem. We have the nQuad from SciPy because we're doing n-dimensional integrals, or in this case, a 2D integral. I don't actually need this, and then matplotlib for a single plot we'll show at the end. That's actually a really good summary of this problem. So import those, and I'm using the units h bar equals 1 here. That just simplifies a lot of the algebra and makes it so we don't have to deal with factors of h bar. So let's look at the actual question of the day. An electron is prepared in a quantum mechanical state with zero average momentum, and a wave function given by psi of xt at t equals 0 is just a Gaussian function. So you have your x-axis here. It's a one-dimensional quantum mechanical problem, and it's a Gaussian wave function. And if I square this, of course, that's the probability density function. That tells me that the probability density function is a Gaussian function. E to the negative x squared over, if I square it, e to the negative x squared over a squared. So a is like the sort of width of this well. And of course, over time, this function will change. We'll get into that, but this is the initial state. Potential is 0 everywhere, so it's a free particle, and it's got an initial state. Then you place a detector at x equals L. So you have your particle, x goes from negative infinity to infinity, and then you have a detector at x equals L. And that's from the electron's initial position. And there's two questions here. And the first one you can sort of solve by hand pretty easily, and we'll go over that. And there's a few things that the computer can help us with in terms of algebra, because I don't like doing algebra by hand. And then part 2 of this question, find the probability of observing the electron. It says it should really say past x equals L as a function of time. So it starts in this sort of Gaussian probability density function. Over time, it's a wave function. It'll spread out. And then your probability of detecting it past the detector, of course, will increase over time as it spreads out. And you can sort of set up an equation for this using the Schrodinger equation. And you get this integral that you can't solve by hand, but the beautiful thing about a computer, of course, is you can do it very easily. So part 1, after how long approximately is the electron likely to have passed the detector? So you would know that the particle starts with 0 average momentum, but it doesn't start with 0 average kinetic energy. Kinetic energy, of course, proportional to p squared. So even though it's 0 average either going right or left, positive or negative x, it's still going to have p squared. So it's going to send off one direction. We just don't know what direction that is. So we can compute the average value of p squared from the wave function, right? You know how to do that. I'll show you how to do that. And then you can sort of use a classical estimation. Momentum is mv, which in this case, if it's moving at a constant velocity, that's an assumption we make. It's ml over t. L is the distance to the detector. And you can sort of compute this. And you can relate these two equations here. T is ml over p, if I arrange for this, but we compute p squared. So t is ml over p squared. And there's only a 50% chance of it actually reaching the detector, because if it starts in this symmetric wave function, it could go off in either direction. So I'm computing sort of hand wavy the amount of time estimate that it would take to reach the detector. This isn't going to be an exact answer, of course, because this is a quantum mechanical problem, but as we'll show at the end, this time gives a good estimate order of magnitude of how long it takes to reach the detector. So for any quantum mechanical operator, you compute the expectation value as the integral of dx. Right here, I'm integrating over space. We're dealing with the position basis of the wave function dx, the wave function itself times the operator here, which is p squared, psi. So I compute this integral here. And of course, this is psi at t equals 0, but I'm assuming that, of course, it doesn't lose kinetic energy, which it can't, because it can't exchange kinetic with potential energy here because there is no potential. So you see there's a lot of sort of hand wavy assumptions being made here, but again, this gives a good order of magnitude guess. So let's define all the variables we need here to compute this integral, because of course psi is just a Gaussian function. This is the derivative of a Gaussian function. This integral you can compute symbolically, and you can do it by hand, but I'll do it in SymPy just to show you how easy it is. So let's define all the variables we need for this problem. Well, we need x, which is position, so I define it using SymPy.symbols x. And the good thing to do in SymPy is make sure you specify all the properties of each variable when you define them, because that will stop it when it runs into weird things. For example, if I just said x and I didn't specify that it was real, it would, if it solves a problem using x, it would give all the different cases. Like if x is imaginary, this is the answer. If x is real, this is the answer. So by specifying this, it just makes SymPy work less hard, and the answers are more clear. And then I define A and L, which of course A is the width of this Gaussian. L is the length of the detector, M is the mass of the particle. And I'm going to define K and K prime and time here. This is for later on, but so ignore these for now. But the main thing, of course, that we need for this is A, L, and M, and they are all real variables and they are all positive. So then I'm going to define and normalize my wave function. Here I just define the Gaussian function, which is the initial wave function specified right here. And then to normalize, I normalize so that the integral of psi squared over all of x is equal to 0. So for that, I'm integrating psi squared over all x, but I'm just dealing with psi here. So I divide by the square root of the integral of psi squared over all x. And by definition, then, if I integrate this over all x, I'm going to get 1. So I define my wave function and the normalization condition, and I look at my wave function, I get e to the negative x squared over 2a squared divided by this normalizing factor here. So I now have the wave function such that if I integrate it over all space, it's equal to 1. So I've normalized my wave function. Now that I have the normalized wave function, I can compute p squared just using directly the formula I have above, which is this here. So I integrate psi times the negative d squared dx squared of psi over all of x. That's exactly what I have written here. It's psi times the second derivative of x, or the second derivative of psi with respect to x. So I differentiate with respect to x twice. That's what this is here. This is SymPy.derivative. Of course, if I just run this on its own, I get the derivative of psi with respect to x twice, then multiplying by psi like this. And if I take the negative of this, I get my integrand. And I integrate this from negative infinity to infinity of x. And that's what I specify here. That gives me my expectation value of p squared. So I compute that, and my value of p squared is 1 over 2a squared. Now you note that this is 1 over meters squared, which is not the same dimensions as momentum, but like I said, I'm using the units h bar equal to 1. So then at the end of the problem, I multiply by h bar or divide by h bar as needed. So now I compute the time t given the equation above, the equation I derived here, t is ml over square root of p squared. And I just compute that, and I get root 2 LAM. So this is my time. But again, you'll note that this is not in units of seconds or in SI units. It's not seconds. I have meters times mass. So this is kilograms meters squared. That's my current units. And I need to multiply and divide by Planck's constant to get the units I want. So since Planck's constant has units of kilograms meters squared per second, all I have to do is divide by h bar. And then the kilograms meters squared cancel out, and I get seconds coming up, and then I get my answer in seconds. So this divided by h bar squared is the time it will take the electron to reach the detector. So that's a rough estimate of the time. Now what we're going to do is we're going to, at all times, from t equals 0 to t equals infinity, find what is the probability of the electron being found past x equals L. So I have my initial wave function, of course, and over time, it's going to move outwards. And the probability of finding it past L is just integrating the square of the wave function from x equals L to infinity. But in order to do that, I need to know what the wave function is as a function of time. And there's an equation that's perfect for that, and that's the Schrodinger equation. So we'll solve the time-dependent Schrodinger equation. We'll find the wave function as a function of time. We'll integrate from x equals L to infinity, and I'll do that at a number of different times, and we'll plot what's the probability of finding that particle at the detector or beyond as a function of time. So the wave function changes in time according to Schrodinger's, which is just this equation here. I d dt of psi equals h psi. So h is a linear operator. That's the most important thing here. You're dealing with Hermitian linear operators. So this equation has a very simple solution. You might have seen this before. I'm going to describe it in depth because it's so important to understand equations, the solutions to equations written this way. And actually it gives motivation as for why the Schrodinger equation is written this way. Because when deriving it, you almost get a solution that you want. So writing it in this way gives you a beautiful solution, right? So in this case, h is minus 1 over 2m d squared dx squared. That's for the free particle, but of course there's many different Hamiltonians for many different systems. And no matter what the system is, the general solution to this equation here, d dt of something is equal to linear operator times something. And there's an I here as well. The general solution to this equation is always given by psi of xt is e to the I h is the Hamiltonian linear operator, times psi of x at t equals 0. And you'll say, oh, I have a linear operator and an exponential. That doesn't, what does that mean? I'm taking a derivative operator, second derivative in an exponential. Well, don't worry, because this is defined. This is defined by definition. E to an operator, e to a linear operator here is defined as the sum as n equals 0 to infinity of that linear operator to the power of n. Of course, you can apply a linear operator over and over and over. So a cubed is just a linear operator applied 3 times over n factorial. So this whole thing is just expanded as this infinite sum. So, this is kind of an annoying way to write the solution, but it is the solution technically. You have a linear operator in an exponential, and then it's written sort of like this. Of course, you wouldn't write it as, you could write it as sum n equals 0 to infinity of, I, h, t, or whatever. But here, this is just a simple way of writing the answer to this equation. But it's not in a convenient form that we can extract what that wave function is. But we know what psi of xt equals 0 is. We know h. So this is in principle the solution that we have. Like I said, it's not convenient. But if we can express this initial wave function here in terms of eigenstates of h, right? So suppose it's the sum of many eigenstates or eigenvectors in the vector case. This is the continuous case of h. And what I mean by that is psi of x at t equals 0 is equal to, well, this is the continuous case. So I'm weighting each of the eigenfunctions, psi e, these are the eigenfunctions of the Hamiltonian. So there's maybe many of them, like it could be sine x, sine 2x, sine 3x. They form a complete basis. There's other different basis functions. These are the basis functions that are the eigenstates of the Hamiltonian. And I'm adding them all together. Remember, an integral is just a sum. And the weight of each one of these functions is dE times the coefficient c of e. This is just like, you could think of dE CE as like, the weight, and then psi e of x as the vector. So you're summing all these different vectors together, and you get the general solution psi of x 0. And this could be any function you want. The beautiful thing is the eigenstates of the Hamiltonian, they form a complete basis. So with all these psi e's, you could write any function f of x sort of like this, right? That's the beautiful thing. And so if I express psi of x 0, this function here, in this form, so if I know all the contribution of each of the basis functions contributing to psi of x 0, then I can write the solution like this. Well, here's psi of xt, what I have written above, eiht, psi xt equals 0. Then I expand it in this format here, right? And then I bring e to the iht inside this integral. So it doesn't work on the dE, it doesn't operate on the CE. It goes to the psi e of x. But because this is an eigen state of the Hamiltonian, if I write my e to the iht in this format, every time h operates on psi e, I just get e coming out of it. So you could show this yourself if you do e to the iht times psi e, and you plug in this, you just simplify all the terms, rather than having h here, you have e here, but it's going to be different for each one of the psi e's because each of the psi e's has its own eigenvalue. So you get this equation here. So if I can express psi of xt equals 0 in terms of these functions here, I can write my general solution like this, right? This is psi of x at any time t. Of course, then you run into another issue. You need the eigenvalues and eigenstates of h, right? You need to know what these psi e's are, and you need to know what the c of e's are. And that's just solving the time-independent Schrodinger equation. So for this, of course, our Hamiltonian is h is minus 1 over 2m d squared dx squared, and we search for eigenstates. H times psi equals e times psi, which if you simplify this equation is the second derivative of psi is equal to some constant times psi. Of course, the characteristic length scale of this problem is a. That's the width of our Gaussian function. So I'm going to do a little trick here to get rid of a for the rest of the problem. Instead of considering x by some units of meters, I'm going to consider x in units of a. So I'm going to multiply this equation by a, and I'm going to redefine x so that x is equal to x over a. So if I say x is equal to 3, that's my new units of x. What I really mean is x is equal to 3 times a. And we get the following equation. D squared dx squared of psi, of course now x is measured in units of a, is equal to minus 2me times a squared psi. And I know how to solve an equation that looks like the second derivative of a function is equal to constant times a function. Well, actually, the equation I know how to solve is the second derivative of the function is equal to minus k squared times the function. Because you take a derivative and a k pops out, then you take another derivative and a k pops out. This is a beautiful equation that you've seen before. And of course, since the energy is positive because you have a free particle, you know that k is positive. So you definitely know the solution to this equation. It's just psi k is equal to e to the I kx. So these are my eigenstates of my system. And it forms a complete basis. These exponentials, as you know, form a complete basis when considering all positive and negative values of k. But remember that a positive value of k and a negative value of k correspond to the same energy. So now we write this. We have psi of x is 0. We sum over all the energy eigenstates with the corresponding energy eigenvalue, but we have k instead of e, and k is negative and positive. Then we get that complete basis. So instead of integrating over all positive e, it's the same as integrating from negative infinity to infinity of all the different k values, c of k e to the I kx. What this tells you, if you identify this formula, is that c of k is just the inverse Fourier transform of psi of x 0 by definition of this equation. So ck is 1 over 2 pi. This is the inverse Fourier transform of this. Integral of negative infinity to infinity, psi of x 0 e to the negative I kx dx. So we know what our ck's are. We have this formula here. We know what our psi k's are here. We have e to the I kx. And from that, we can find the wave function at any time we want. So first, let's define psi. Of course, now we're using x as x over a, measured in units of a. So our new initial wave function is just e to the negative x squared over 2. Then we normalize again like we did above. Now we define the psi k of x, and we get the ck's. So psi k is just like I wrote above, e to the I kx, what I have here. Ck is 1 over 2 pi, this formula here. Integral from x goes from negative infinity to infinity of psi, which is just psi of x 0 here. Remember, that's the initial state, times psi k dot conjugate. So psi k is e to the I kx. The conjugate of that is e to the negative I kx, which is what you see in this formula here. And we now have our psi k and our ck's. So psi k is just what you think. It's e to the I kx. Those are our eigenstates, and our eigenvalues are this here. So for every one of these, I multiply by this, I take that integral, and I get my initial wave function psi of x 0. Now we should get our initial wave function if we integrate from negative infinity to infinity, dk c of k e to the I kx. So let's compute this integral. We should get psi of x 0. I'm just going to plug that directly in. K goes from negative infinity to infinity and simplify it. And sure enough, we get our initial wave function here. That is the same as psi. So now that we've solved for both the eigenstates and the eigenvalues of the system, I can write psi of xt as a function of any time that I want, the wave function at any time, by integrating over energy, ce e to the I e t, psi e of x. This is the equation above, but I solved them in terms of k here. So in this case, I integrate from negative infinity to infinity in k. I know what my ck's are. This here is just e to the iet. Remember that e is k squared over 2m here. And then I know my psi k's because I solved for them above here. So in principle, I could compute this integral for any value of x and t that I wanted, and I can compute the wave function at any time. But remember, that's not exactly our problem. Our problem is to find what the probability of the particle being found beyond x equals L is as a function of time. So now that we know this wave function, we can compute this. So what is this exactly? Well, p of t, the probability of finding it beyond x equals L as a function of time, is just the integral from L to infinity of the modulus of the wave function, the square of the wave function, just integrated over this range. So remember that our wave function is symmetric in x. So the probability of it being found beyond x equals L or beyond x equals negative L is just 1 minus the integral from negative L to L of psi squared. And again, because it's symmetric, I only want it being found in the positive x region, so I multiply it by 1/2. Think carefully about that if you don't quite understand what I said, but all I'm doing here is I'm exploiting the symmetry of the wave function to rewrite this infinite integral bound as this nice symmetric integral bound. And as you'll see in a second, it is very handy. So to find the probability as a function of time, you'll note that this is the only thing that we need. So we just need to solve this integral here. And I'll expand it as follows. The integral negative L to L of psi squared dx will integrate from negative L to L. And now I need to take psi times psi star. Psi times the conjugate of psi. Well, psi is just this integral here. The conjugate of psi is this integral here, but replacing I with negative I. And also taking the conjugate of c and taking the conjugate of psi k of x. So that gives me the conjugate of this wave function here. And I'm going to need to express it as a different integral. I'm not going to integrate over k both times. One of them is going to be over k. One of them is going to be over k prime. So I'll just plug this into this equation here. So negative L to L of psi squared dx, negative L to L. Then I have my two integrals, one over psi and one over the conjugate of psi. So one integrating over k, one integrating over the dummy variable k prime here. Ck, e to the I k squared t over 2m, psi k of x, that's the first one. And then, of course, the conjugate wave function, where I take the complex conjugate of all these things here, and I'm using the variable k prime to do that integral. And I get this triple integral here. So before we try to solve this triple integral on a computer, you'll note that we have all the pieces of the puzzle, and we could just plug these in and solve it. We should always try to simplify it as much as possible to reduce the computation time. So the big thing here is that we have a triple integral, and that takes a long time for a computer to do. So maybe we could reduce this. Maybe there's a way to reduce this to a double integral or a single integral. Well, it turns out that because of the simplicity of the Gaussian wave function that the particle starts in, that's a nice function, we can reduce this integral here to a double integral. And I'll show you how to do that. So let's simplify the expression. Note that psi k of x, it has a really simple format for the free particle. It's just e to the I k x. So integration over x is really easy to do in this triple integral. The only things that depend on x are psi k and psi star k here. So we can integrate over these two functions alone and leave all the other coefficients by themselves. So I'll rewrite this integral, just grouping everything in x as a single integral here, and this is an easy integral to do. So we'll evaluate the center integral, and I'm going to define all the conjugate wave functions. So anything that's star, the complex conjugate, I'll put an underscore c to denote that, and anything with a k prime, I'll use a p for that. So ck prime conjugate, which is just this function here, is defined here. And same with psi k prime conjugate, same thing with psi here. So this is just ck, except instead of having a k, I put a k prime. So I substitute k prime in terms of k, and I take the complex conjugate, and I do the same thing for psi k prime c. And if I just look at these two things, c underscore k prime conjugate, because ck was just a real variable here, this is just the same thing, only k instead of k prime. Same thing with this function here. I take the complex conjugate, so it's e to the I kx. Now it's e to the negative I k prime x, and it's the complex conjugate, of course. Now we can evaluate this integral really easily, and I'll save the result in a variable called r. So this integral is r. And I just integrate psi k times psi k prime c, which is just this function here, from x goes from negative L to L. And then I do a little bit of rewriting in terms of sine and sinc, and that helps simplify the function. So now I get my result R here. And if I don't do that, you'll note if I just look at this, it gives it in this sort of interesting format. So by rewriting it in terms of sine and sinc and doing some simplification, I get the really nice format which I have here, 2L sinc L k minus k prime. So now I know what this is, I know what ck and c, the complex conjugate with k prime is, I know what this is, and I can rewrite the integrand of this double integral as a numerical function. So I plug in k and k prime and time and mass, plug in all these variables, and I can just get a number for the integrand, or in this case, a complex number for the integrand. Then I integrate it from negative infinity to infinity in both cases, and I'll get the answer to the integral that I want. So let's define the integrand like this, and I'll simplify it and we'll look at it. So this is what our integrand looks like. This is what everything here all put together looks like. And I have to integrate this from k goes from negative infinity to infinity, and k prime goes from negative infinity to infinity. And I plug in a specific value of time in here, and then I get the probability. I compute sort of this integral here, which is this integral here, and I take 1/2 of 1 minus whatever that integral is, and I get my probability of it being detected beyond that detector. So you'll note that the integrand is a complex function here, but we know that the result of that integral has to be a real number. So it means that the complex component of this is going to evaluate, if you integrate it, to 0. So we only care about the real component of this integral when we integrate it, because we know that the complex part has to evaluate to 0. So we'll take the real part of this integrand, and I get this function here. And if I plug in L, K, and K prime, and mass, and time, I can compute this integrand. And so for a given value of time and mass and L, I can integrate this over all K and all K prime and get a value. So we need to integrate it over all of K and K prime. So what I'm going to do is I'm going to create a numerical function from this simpi expression. I'm going to lambdify it. That's what simpi.lambdify does. K, K prime, and then L, M, and T. So I plug in all these things and it just returns a value. And that's my integrand f. And of course I can just plug in 5 sort of things here. Suppose I just plug in 1, 1, 1, 1, 1. And it will just give me a number. And I need to integrate this over all of K and K prime for a given value of L, M, and T. So for example, here's L equals 1, M equals 1, T equals 5. So by the way, L equals 1 means that L is equal to the width of that wave function, because this is measured in units of A. So I define these here. And let's sort of look over K space, K and K prime. Let's see what the thing we have to integrate in 2D looks like. So I'll create a K grid and a K prime grid. Those are the two integrating variables. And let's just plot what our integrand looks like, what we need to sum over. So I can do that here, and I get the following looking thing here. So you can see that if I put a color bar up, it's sort of centered. Everything here is 0, and then it goes to negative values, and then it oscillates to positive values. And I need to integrate this over all space. And it decays to 0, so they have this sort of local region you need to integrate over. And if I sum that all together, I'll get a probability. So I have a function here to compute the probability, which is just doing a double integrand over this integrand function. A few things to note. You'll note that in the integrand above, t divided by m always shows up together. So if you look here, t over m always shows up. There's never t or m separate. So what I can do is set m equal to 1, and then I can put in different values of t. So for example, t equals 2. And then what I'm looking at really is this integrand as a function of time divided by mass. So that's interesting that time and mass are linked. And the smaller the mass, the faster the wave function is going to propagate, which is what you expect for a particle of a given momentum. So what this function does here is it integrates this over all of k and all of k prime, and you get a corresponding probability. You solve your integral. You plug it in up here, and you get your probability as a function of time, but that also depends on the length, L, how far away that detector is. So it's just 1/2 of 1 minus the integral of integrand f, that's the function we know. You'll note that k goes from negative infinity to infinity. K prime goes from negative infinity to infinity. The additional arguments that the integrand f takes is L, M, and T. That's the same order that I lambdify it above, L, M, and T. And I'm going to use 100 subdivisions in the quad routine. Remember, quad is a specific numerical routine to find the integral of a function. So I'm giving this additional option that I want to use 100 sort of subdivisions. The reason for that is that this is a highly oscillatory function. And if I plot this, for example, at t is equal to 20, and I look at this function, you can see that it oscillates really quick. And that's a real pain for these integration methods that you use numerically when you have a really fast oscillating function. So by using more subdivisions, it allows it to solve the integral more accurately, but also faster as well. So I plug in a value of t, I plug in a value of L, and this integral gets solved. So let's plug in L equals 5. So our length scale of x equals 1 corresponds to a. So L is 5 times sort of the width of that Gaussian function. And let's find the probability of it being detected past x equals L for L equals 5. So here I have a number of different times here, and I'm going to vectorize compute probability. So what it will do is it'll take each of these values of t, it'll plug it in, and it'll store the result in a NumPy array. And that'll give me my probability for each one of these times. I'm plugging L equals 5, corresponding to this argument here. And because this is sort of a small box, bounded definitely between -5 and 5 and -5 and 5, I'll use my limit of 5 here. So that took about a minute to run. We have our times and we have our probability of being detected past x equals L. And we can plot them. And what I'm going to do, remember earlier we find that the time it takes to get past the detector using this sort of classical approximation was t equals root 2 LAM. Remember a equals 1 in our case. And we're computing the probability as a function of t divided by m. So let's add a line at t divided by m equals root 2L. So here I'm plotting 5 times square root of 2. And you can see that our probability of observation beyond x equals 5a, it starts at 0. So the particle's localized sort of near the origin, and then it starts to spread out. And at a certain point, you get the sort of rise of probability, and then it sort of decays like this. And it will peak at 0.5, because remember that it goes in one direction or the other, essentially. And so this is sort of going to rise probably up to about probability of 0.5. And we see that the line corresponding to the time that we computed corresponds to that rise, that sharp rise in probability sort of in the center. So in terms of an order of magnitude, it does give us a pretty good estimate of when the particle passes that detector. Anyways, I hope you enjoyed this video. If you made it to the end, that's awesome. Congratulations. Please be sure to like and subscribe, join the Discord server as well, and I'll see you next time.